Assalamualaikum warahmatullahi wabarakatuh. Okay, today I want to present our chapter 2 here in topic of fluid in relative equilibrium, hydrostatic pressure and buoyancy. Okay, fluid in relative equilibrium, hydrostatic pressure and buoyancy. Okay, so first we have 4 subtopics here: pressure head, pressure measurement, hydrostatic force on plane surfaces, and buoyancy and stability. So the first and second topic I will discuss in part 1, and the other topic, hydrostatic force and buoyancy and stability, I will discuss in part B. Okay, pressure is defined as a normal force exerted by a fluid per unit area. Pressure is defined as force per unit area and with a unit Newton per meter squared, which is also called a Pascal PA. That is, 1 Pascal is equal to 1 Newton per meter squared. Okay, 3 other pressure units are bar, standard atmosphere, and kilogram force per square centimeter. Okay, so 1 bar is equal to 10 power of 5 Pascal, or 0.1 megapascal is equal to 100 kilopascal. And the other unit for pressure is 1 atmosphere and also 1 kilogram force per centimeter cube. So this is the conversion unit from the bar to Pascal to atmosphere to the Pascal and kg force per centimeter squared for Pascal or bar or atmosphere. Okay, this pressure between the two, okay, weight 150 pound and 300 pound. Okay, so we know that the equation for the pressure is equal to W divided by area. So W is the weight of the this person, this 2%. So we have the weight for the 150 pounds divided by the area. So the area is the same between these 2%. So we get the pressure for first person here, we get the 3 psi. The psi is the in unit, USA unit, but we in our chapter fluid mechanics we use the SI unit. Okay, for the other person here, so we get the pressure on 6 psi. So the normal stress or pressure on the feet of a chubby person is much greater than on the feet of a slim person. Okay, the actual pressure at a given position is called the absolute pressure, and it measures relative to absolute vacuum. So the most pressure measuring devices, however, are calibrated to read 0 in the atmosphere. Okay, and they indicate the difference between the absolute pressure and the local atmospheric pressure. So this difference is called the gauge pressure. Okay, so pressure below atmospheric pressure are called vacuum pressure. So this is the vacuum pressure. Pressure below atmospheric. So this is atmospheric pressure, called vacuum pressure here. And they are measured by vacuum gauge that indicates the difference between the atmospheric pressure and the absolute pressure. Okay, usually we use this equation. Okay, P gauge is equal to P absolute minus by P atmosphere. So P vacuum is equal to P atmosphere minus by P absolute. Okay, so we look at this figure here. Okay, P atmosphere. P vacuum is equal to P atmosphere minus by P absolute, where we get the P vacuum. To get the P gauge here, P absolute, okay, P absolute here minus by the P atmosphere here. Okay, so this equation for this figure and this equation for this figure. Okay, so example 2.1 here. So the vacuum gauge connected to a chamber with 5.8 Pascal at a location where the atmospheric pressure is 101.3 kilopascal. Determine the absolute pressure in the chamber. So we use this equation. P absolute is equal to P atmosphere minus by P vacuum. So we get the 101.3 kilopascal. Okay, this is kilopascal. Okay, so okay, this is kilopascal. This is Pascal. Okay, so just convert the kilopascal to Pascal. So we get the 101.3 times by 10(3) Pascal minus by 6.8 Pascal. So we get this equation. Okay, so example 2.2. So find the absolute pressure in the kilopascal unit if barometer shows the reading of 60 kilopascal, given the barometer reading at sea level is 740 mmHg and specific gravity of mercury is 13.6. So the gauge pressure given the value is for the P gauge is 60 kilo per pascal. Barometer reading is 740 mmHg and the mercury specific gravity Sg for the mercury is 13.6. So note that the P atmosphere is density of mercury times by G times by H. Okay, PM is the mercury density. So just put all the value here. So we get the P atmosphere value. So and use this equation. Okay, P absolute is equal to P gauge plus P atmosphere. So you just use the P gauge 60 plus 98.73 kilopascal. So we get the 168.73 kilopascal. Okay, we get the value here. So the variation of pressure with depth here. So pressure in the fluid increase with depth because more fluid rests on deeper layers and the effect of this extra weight on the deeper layer is balanced by an increase in pressure. So the pressure of a fluid at rest increases with depth as a result of added weight. Okay, to obtain a relation of the variation of pressure with depth, consider a rectangular fluid element in equilibrium. So this is part of the, so this is assuming the density of the fluid R to be constant, a force balance in the vertical Z direction give. Okay, so we know that the force using this equation. Okay, this equation for the force here. Okay, F is equal to M is the mass times by A is acceleration is equal to 0. Okay, so using this, okay, this object here, so P2 they have the arrow direction is okay to upward, so the upward is the positive here. So P2 times by delta x here using the x directions and the minus P1. Okay, P1 is downward, the direction is the downward, that's why we use the negative here, P1 times by delta x here because this is on x direction. Okay, vertical balance in the vertical z direction the give, so sorry, this is y direction, okay, x direction. Z dash given, so the Px, okay, and the delta Z here. So the objects in object of this fluid, so we use the density times by G times by delta X, delta Z is equal to 0. Okay. Okay, so look at the variation of pressure with the depth here. So if we take point 1 to be point 1 here, to be at the free surface of liquid open to the atmosphere, where the pressure is the atmospheric pressure. So where the pressure is the atmospheric pressure, P atmosphere, then the pressure at the depth H. So the H here from the free surface become P2 here. So this is the P1. Okay, P1 is equal to P atmosphere because it's open to the atmosphere here. Okay, and the P2 here. Okay, so we use this equation. Pressure is equal to P atmosphere. Okay, times by the pressure at using this depth H depth. That's why we use the P atmosphere. Pressure at this point is equal to P atmosphere plus the pressure at this depth, rho GH here. So P gauge is the rho GH. Okay, so we use this equation. Okay, so look at the variation of pressure with the depth. So we have the PA, PB, PC, PD, E, F, and G with the same level here. Okay, with the same H. That's why the PA is equal to pressure at A is equal to pressure at B, equal to pressure at C, equal to pressure at D, equal to pressure at E, F, and G. Okay, so that's why with the same atmosphere at the same depth here, that's why the PA is this one, P atmosphere plus the rho GH here. Okay, P atmosphere is open to the atmosphere here. Okay, so we get the PA, PB, PC until to the PG here is equal to P atmosphere plus rho GH here. But at the pressure H here to the pressure I here, okay, pH is not the same as the PI here. Okay, because pH, okay, we have the pH, okay, pH with this depth, okay, so the H plus the mercury here. Okay, pH is the P atmosphere plus density of, okay, water GH water. Okay, H this one plus rho mercury GH mercury. Okay, this is for the pH, but for the PI here we have P atmosphere plus, okay, we call here is H2. Okay, this is HW. Okay, we have this is a H. This is HW. Okay, this is HM. Okay, so this H2. So this is rho G H W. Okay, sorry. So we have the PI here. Okay, PI here is PI equal to P atmosphere plus rho water G H W plus H2. Okay. Okay, pressure in the fluid at rest is independent of the shape of cross-section of the container. It changes with the vertical distance but remains constant in other direction. Therefore, the pressure is the same at all points on a horizontal plane in a given fluid. Okay, so this is the plane here. Since there can be no shearing force for a fluid at rest and there will be no acceleration force, the sum of the forces in any direction must therefore be zero. The forces acting are due to the pressure on the surrounding and the gravity force. Okay, look at this point here. So force due to the px. Okay, this is direct x direction. Okay, this is for x direction. Okay, so Px, force due to the Px is equal to Px times by area of ABC. Area of this A, B, E, F here. This is for the direction of x, Px here. Okay, so we get the Px times by dy dz. So horizontal component of force due to Ps is negative Ps times by area ABCD sine Q. So we get this equation. Okay, as Py has no component in the x direction, so the element will be in equilibrium if Px dy dz plus is negative Ps dy dz is equal to 0. Okay, Px is equal to Ps here. Okay, there's no x direction for the Py. So just Ps is equal to Ps. So this is the y direction. Okay, the y direction force due to Py is equal to this one. Okay, and dz are very small quantities. Dy, dx, dz is negligible in comparison with other two vertical force terms and the equation reduced to this one. So the Ps is equal to is negative Ps times by area of A, B, C, D, E cos T. Cos T, we get the equation. So this is for the y direction. So force due to weight of element is equal to negative mass times by G. OR is the radius. Okay, so we just know that F is equal to ma, or force due to weight of element. So we get this one. Okay, so this pressure at the point is small in all direction, same in all direction. This is called the Pascal law. This applies to fluid at rest. Okay, so look at this example for the with the this one, what by the small force by the application of Pascal law. So this is the terms of Pascal law. So at the same level here, so P pressure at 1 and pressure at 2 is equal. Okay, using the Pascal law. So this is Pascal law. So pressure at 1 is equal to pressure at 2. Okay, so we know that the pressure is F1. Okay, force at 1 times by area of 1 here. Okay, this one. Okay, force here. So we get the F2, F1. So from this equation we convert to this equation. So this is called Pascal law. Okay, example 2.3. So this example, you can look at this figure. Okay. The example is for using this figure. Okay, so pressure at 1 is atmospheric pressure. We get this one. Okay. What is the pressure difference in 1 meter of seawater compared with 100 of seawater? So the density of the seawater, okay, this one. Okay, P1 is atmospheric pressure is equal to 1.013 times by 10 power of 5 Pascal. Okay. So with the P1 at atmospheric pressure, this is the pressure. So at 1, so pressure at point 2, we know that P atmosphere is equal to P1 here, so plus the rho GH here. So you just put all the value here, so we get this value. Okay, at 1 meter, at 100 meters, so we just put all the value here using the different H. So we use the 100, so we get the value here. So the pressure difference, we get the just minus pressure at 100 meter minus by pressure 2 at 1 meter. So we get this value. Okay, so this is the variation of pressure with depth. Okay, with depth, with 3 different depth and the 3 different fluid. So we get using this equation. Okay. Point at air pressure at 1 is equal to pressure atmosphere plus pressure at fluid 1, pressure at fluid 2, and plus pressure at fluid 3. So that's why we get P atmosphere plus ρ1 GH1 plus ρ2 GH2 plus ρ3 GH3. So we get the pressure 1. Okay, instead of fluid layers, the pressure change across a fluid layer of density ρ and height h is ρ GH here. Okay, so look at example here. Figure shows 4 different fluid inside a glass container at 20 degrees Celsius if atmospheric and absolute pressure at the surface and bottom are 101.03 kilopascal and 231.3 kilopascal. Find the specific gravity of olive oil. So we know that the SAE oil here with the height of 1.5 meter, water 2.5 meter, olive oil 2.9 meter, and mercury 0.4 meter. So we given the P atmosphere is 101.3 kilopascal and the P absolute is equal to 231.3 kilopascal. Okay. So refer chapter 1. Actually, this is you can refer from other book, reference book, from other reference book. Okay, so we use the equation of the P as E is density, okay, as G is specific gravity of oil times by density of water times by G times by the H here. So we use 0.62. So we find the SE oil. This is from the, you can find from the refer from the other reference book to get the SG of SAE oil. So we get the SAE oil is this one. Okay. So raw water here, density of water, we know that Sg of water, specific gravity of water is, we just use the density of water 1000 times by the G here and times by the height of the water, depth of water. So we get the value of PW is this one. And the P olive, okay, so we know that the Sg olive is times by rho W GH. Okay, we don't know the Sg olive, okay, times by, because the olive is not included in the table, chemistry table that you have learned in chapter 1 and also you learn in chemistry. So just times by 1000 density of water times by G 9.81 and times by H 2.9. So we get the P olive is 28449 Sg olive. Okay, 28449 times by Sg. So the P mercury, we know that the density of the mercury, the Sg mercury is, okay, 13.656 times by 1000 times by 9.81 times by height. So we get this one. Okay, so know that the P absolute is, okay, use this equation for all the equation at the absolute at the part of the below of the mercury. Okay, so P atmosphere plus P SAE oil plus P water plus P olive and plus P mercury is equal to P absolute. We know that the P absolute, okay, the P absolute, okay, P absolute is also 231.3, okay, kilopascal. Okay, P absolute here. Okay, P absolute. Okay, so you just convert the P, okay, just change the P to this, just at the left hand side, and the P atmosphere you just convert to this side and also to this side and to this side, okay, and to this side. So you get the P absolute minus by, okay, this change to right side here. So P absolute minus, okay, this is positive, go to the right side, we get the negative here. Okay, so negative P atmosphere, okay, this is also negative. Actually, this is also negative here. Okay, so negative PSE. So actually for these equations, we get the P olive is equal to P absolute minus P atmosphere minus PSE SAE minus PW minus PM. Okay, so just put all the value here. P absolute is this one, okay, P atmosphere or this one, and PSE is this one, PW is this one, and PM is this one. Okay, so also we get the P olive, okay, we get the value of this one, okay, please calculate this, we get the X value is equal the P olive here, okay, P olive you change to here, we get the 28449 times by Sg olive. That's why you get the Sg olive 1.4. Okay, just to calculate this all value, minus this one, minus, and you get the x. This value is equal to this value. Okay, P olive. So that's why you can get the 1.4. Okay. So manometer, types of manometers: simple, U-tube manometers, difference manometers, and inverted manometers. Okay, so simple U-tube manometers, so like this one. Okay, so using the same Pascal law, you must use at the point at 1 is equal to point at 2. Pressure at P2 is pressure at point 2, so we use this equation. Okay, so we get this equation. Okay, also same as this. Okay, look at this. Okay, from this one. Usually mercury is used to measure high gauge pressure, not suitable for gas pressure. So look at this figure. Consider point at this side. Okay, point at this side here, and pressure at this side here. So we call this is P left, pressure at left. At this side we call the P right. Okay, so consider left and right side. So where Px left, okay, Px left here is equal to pressure of A, okay, pressure at A plus pressure of fluid here. Okay, we get this equation here. Okay, so we get this equation here. Okay, for the P at this side here. Okay, at this side. Okay, at this side here, we look at the P right here. Okay, P right. This is P here. Okay, so we have at this part, PB is equal to P atmosphere times by the rho G H1 and H2 here. So we get the P atmosphere plus density of fluid B at B here plus G plus minus G, times G times by H1 plus H2. So we get the P atmosphere is 0 as datum, therefore. So we get the PA plus density A times by GH2 is equal to rho BG. So until we get this equation. Okay. So example 2.5, using the equation that I teach the previous slide. You learned from the previous slide. So calculate pressure at A. To find the pressure at here, to find the PA here. Okay, PA here at A in kilonewton per meter squared. If H1, okay, H1 is 50 mm, H2 is 120 mm. Density of A here, okay, density of water is 1000 kg per meter cube, and density of B here is mercury. Okay, this is water and this is for the mercury here. Okay, so consider left and right side of manometers. So Px left is equal to Px right here. So where left is equal to, okay, look at the left here. Okay, at the left, this is a left, this is a right. Okay, so left PA plus rho W GH2. Okay, so we get the value of the pressure at left. Pressure at right, so is equal to P atmosphere plus rho mg H1 plus H2. Okay, so we get this value. So we know that, and we get this value. Okay, after you calculate, so we get this one. So using the Pascal law, so you must use this equation. Ps left is equal to P right. So just put all the left here. Okay, the left and the right here. Okay, you just put to this equation and also this equation. So we get the PA plus 1177.2 is equal to P atmosphere is 0 plus 2261 4.012. So we get the PA is this value. Okay, so look at the pressure measurement at example 2.6, measuring pressure with a manometer. So a manometer is used to measure the pressure in the tank. The fluid used has a specific gravity of 0.85 and the manometer column height is 55 cm as shown here. So if the local atmospheric pressure is 96 kilopascal, determine the absolute pressure with the tank. Okay, so pressure measurement to find, we want to find the pressure in this tank here. Okay, we know that the SG of this fluid is 0.85. Okay, find the pressure at A and pressure at B to get the pressure inside this tank here. So we know that P atmosphere is at this side is 96 kilopascal here. So look at this given. Okay, so we know that the density of fluid, okay, SG of fluid. Okay, to get the density of fluid, so you must use the SG, specific gravity of fluid, times by the density of water. So you just times 0.85 here times by 1000 kg per meter cube. So then you get the density of fluid. Okay, so we know that you use this PA is equal to B here. Okay, using the Pascal law, so you must take this point is point A and this is as point B here. So using the Pascal law, PA is equal to the PB. Okay, so you just using the, okay, so PB here is a P atmosphere plus rho GH here. Okay, so this is equal. Okay, so rho GH here. Okay, so the P atmosphere we know that 96 kilopascal. Okay, this is density of fluid is this one. Okay, so you must times by the 9.81 and the H here is 0.11 meter. So this rho GH is in unit Newton. Okay, Newton or Pascal. Okay, so to convert the kilopascal to the same as this unit, so you must using this convert unit to get the kilopascal. That's why you must use this conversion unit to get the kilopascal. So at least you get the PA is 100.6 kilopascal here. Okay, so you must know the how to convert the unit from the Newton or kilopascal to pascal. Okay, if you not convert here, you just use the Newton, so you just convert here to the pascal. Okay, only for the pascal and the Newton, not kilonewton. Okay, so if this is convert to pascal, so you have 96 times by, okay, or you can just convert from this here, you get the 96 times by 10 power of 3 pascal. Okay, okay, if you use the pascal, so these equations you no need to convert the to kilopascal. Okay, so you just use this equation in pascal. Okay, pascal is equal to the Newton. Okay, Newton meter per meter square. Okay, so you get the unit for this one. If you no need to convert to kilopascal. Okay, if you not convert this value to kilopascal, so you must use this to convert to the pascal. Okay, so which one you want to convert? if you want, no need to convert here, so you must convert this to kilopascal. Okay, so you get this value. Okay, so pressure measurement at differential manometer. Okay, so this is the differential manometers. Okay, so they have manometers of at A here and also at B here. Okay, tube manometers, the previous slide is open to the atmosphere, but these differential manometers, they have a pressure at A here and also the pressure at B here. Okay, using the different fluid here. Okay, measuring the pressure drop across a flow section or a flow device by a differential manometer here. So point 1 and at the point 2 here. Okay, so you must. Okay, so pressure measurement to at this side here, a relation for the pressure difference P1, okay, at point 1 minus by point 2 here can be obtained by starting at point 1 with P pressure at 1 here. Moving along the tube, moving along this tube, okay, moving along this tube by adding or subtracting the rho GH terms until we reach point 2 and setting the result equal to P2 here. Okay, so look at this. Okay, look at this. Sorry. Okay, at this line here, okay, using the Pascal law. So PA is equal to PB here. Okay, this is using the Pascal law. Okay, so PA, pressure at A is equal to pressure at B here. So we get this equation. Okay, so and then you must look at the left side here and the right left hand side. Okay, you look at the left side and this is right side. This is left. Okay, this is right. Okay, so this is left. Okay, this is for the left here. Okay, pressure at 1. Okay, plus the density 1 times by G. Okay, the gravity times by A, because the fluid is the height of this fluid. From this point to this A here, they have the A plus the H. Okay, that's why you get this left side. Okay, and look at the right side here. Okay, right side here, this one. Okay, right side. Okay, so this is right. Okay, so at the right here, we just look at the point B here. Okay, pressure at B. So pressure at B have the pressure 2 here. Pressure 2 plus the pressure of A here. So that's why the fluid 1 plus the times by G A. Okay, the height of this fluid is A times by the rho 2 GH here. Okay, that's why we get this one. So just calculate these equations until you get the P1 minus by P2, density 2 times minus by density 1 times by GH. Okay, so we get this equation for these differential manometers. Okay, so we get this. Okay, so look at this figure. Okay, used to measure pressure difference between 2 points. We have the 2 points here. Okay, this point is for left. Okay, this is left side. Okay, this is look for the right side. Okay, look at the left side here. Okay, left side. We look at the left side. Okay, left side we have pressure at A, okay, plus pressure at this fluid here. Okay, PA plus density A times by G times by height H2 here. So we get the PA plus density A times by GH2. Okay, so look at the right. Okay, look at the right here. Okay, so they have the PB plus the density of this one. Okay, PB plus GH1. Okay, sorry. So they have the H1 here. Okay, GH1 plus the rho A here. Okay, density of A. Okay. Okay, because this is the same fluid here. Okay, density A. Okay, the same fluid. A G H3 minus by H1. So you get the H2 here. Okay, we get this one. Okay, PB times by GH1. Okay, GH1 is the density of this fluid, the different fluid, density of B. Okay, this is the same fluid as this one. So that's why we get the density A times by G H3 from this one to this one, H3 minus by H1. So we get this one. So you just put this equation to this using this Pascal law. So we get the PA plus rho AGH2 is equal to PB plus rho BGH1 plus rho AG times by H3 minus by H1. So this is at this side. Okay, and this at this side here. Okay, until you get this equation. Okay. Okay. So example, look at the example for this figure. Figure below show differential manometers used to measure pressure inside a pipe. If PA here, okay, the PA minus by PB, okay, PA minus by PB is equal to 120 kilopascal. Find H, okay, to find H here, okay. So using the Pascal law, so this X here, so at this left and X right here is must equal using the Pascal law. Okay, so consider left and right side of manometers. So we use the PX left, PX right here. Okay, so PX left is equal to, okay, PX left here, PA, okay, pressure at A plus pressure fluid here. Okay, so rho A times by G H, okay, to H here. Okay, that's why you get HA plus H. Okay, we don't know the height of this one. Okay, HA times by the H. Okay, to PX left, PA pressure at A times by density of water times by 9.81 HA plus H. Okay, we don't know the H is what is the HA, the value of HA. So in this equation is in terms of PA plus 9810 HA plus 9810 H. Okay, this is using the equation for pressure left. Okay, pressure at right. Okay, look at the pressure at right here. Okay, they have the PB plus the P density of water, pressure at water here, and the pressure at mercury here. Okay, they have 1.6 meter. Okay, from between PB to P here is 1.6 kH here. So look at the right here, PB plus density of mercury times by G times by H, okay, plus density of water G times by HA plus HB, okay, HA and HB here, okay, HA and HB, this is, okay, okay, they have H, so H2, H3, H1, okay, you just use this equation to take HA, HB is H1, H2, H1 here. So you get this using this equation to this one. So you get the HA plus HB. Okay, so we get the, you put all the value here, and then in terms of right is in this one. Okay, sorry, so we get the, okay, for this one. Okay, so we get the terms of x right here. So we get PB plus this one for P right. So just equal the pressure at X line using the Pascal law. So P left, okay, Px left equal to Px right. So we get this one, Pa for the P left and the pressure at right here. So we get this one. Okay, so we get the Pa minus by Pb here in terms of HA. HA is, okay, HA is H1 minus by HA. So we have no HA and also no H. We have the H only. So we get the H is 0.844 meter. Okay. So this is inverted manometers. Okay, so inverted manometers, we have two pressure A and pressure B, and we have density of air here and the density of water here, A, and the density of air. Okay, so this is X here. Okay, with the H1, H2 and H3. So we get the equation for this one is using the Px left and the Px right here. Okay, X left and the X right here. Okay, where Px left, so we include the Pa minus because this is side to the upward and then downward and upward, the direction of the flow. Okay, from this one upward to this one. So that's why Pa minus by density of A times by GH2. Okay. Okay, and also the minus by Pa here. Okay. Rho GH1 here. Neglect Pa. So neglect Pa here. So, okay. Density of here. So if you neglect Pa here, so they have just only have this equation. Okay, so if they neglect Pa, because we just assume there as a 0 here, so they have neglect. Okay, so just only have this equation. Okay, the P right here, we have the Pb. Okay, Pb minus by Pa times by GH3. Okay, at this side, minus by the PAGH1. Okay, the minus here. Okay, so they have no PA here, so the neglect. So we have the PB minus by rho A times by GH3 plus H3 times by H2 here. H3 by H1. H3 plus H1 here. So we get this side here. So PA is minus rho A GH2 is equal to PB minus by PA GH3 times H1. So we get the difference P1 PA minus by PB is equal this side. Okay. So just an example of 2.8. So figure below shows inverted manometers used to measure pressure inside a pipe. Okay, find the pressure difference of PA minus by PB. Okay, so look at the consider left and right side of manometers, PX left and PX right. So where P left, we have the PA minus by PW is water times by GHA. So we get the PA minus by 1000 times by 9.81 times by 1.625. We get this value. So we get the PX left is PA minus by 15941.25. Okay, at PX right, so is equal to PB times by PX GHB times minus by PW. Okay, because they have two different fluid, water and also the X here. Okay, so we get the PB SG of X fluid times by raw water GHB, using the raw water here GCHC. So put all the value here, so we get the X right, PX right is get the this one. Okay, PB minus by 10791. Okay, so equal the pressure at XX line left and right side. So we get the PA and the PB here until we get the value of this one. Okay, that's all. So this is multi-fluid. Okay, they have the multi-fluid. They have the three different multi-fluid here. Okay, the water in the tank is pressurized by air and the pressure is measured by a multi-fluid manometer as shown in the tank. It's located on a mountain at an altitude of 1400 m where the atmospheric pressure is 85.6 kilopascal. Determine the air pressure in the tank if H1 0.1, H2 0.2 and H3 0.35 meter. Take the density of water, oil and mercury to be 1000 for water, 850 for mercury and 13,600 kg per meter cube for mercury. Okay, so using the P atmosphere, we know that the give you the P atmosphere is the give you atmospheric pressure is this one. Okay, so that's given 85.6 kilopascal. So H1 is equal to 0.1 meter, H2 is 0.2 meter, H3 is 0.35 meter. Density water, density oil and density of mercury. Okay, so look at the, we just use this. Okay, part of this. Okay, using this multi-fluid here. Okay, so at the pressure 1 here and the pressure 2 here. Okay, using the pressure 1, okay, and the pressure 2 here. So this is pressure 1. Okay, and this is pressure 2. Okay, so pressure 1, okay, we get the pressure 1 is PW here. Okay, then P1 plus pressure in water here. Okay, PW times by GH1. Okay, the H1. Okay, plus raw oil here. Okay, so raw oil is GH2 here. Okay, minus by mercury here. GH3 is equal to P atmosphere. Okay, this is the P atmosphere. Okay, so just put all the, just use this equation. So we get the P1 is 130 kilopascal. Okay, so you get the unit here. Okay, so because this is the multi-fluid, so this is the atmosphere here. Okay, so the P1 to the P atmosphere here. Okay, so or if you don't understand here, you can using this equation Pascal law here, using this. Okay, x left, the x right. Okay, x left, the x right here. Okay, so you just use the P x left equal the P x right. Okay, so you can use this one also, or you can use this equation for the at this part here. Okay, at this part here, at the same level here. Okay, at this part to this part, they have the only part of this one. Okay, so or you just give this of this one. Okay, so you can use this equation for px left or px right here. Okay, no need to use this one. Okay, okay, or you can use this one. Okay, so this is P2 here. Okay, P atmosphere here. Okay, you just P2 here. So P2 just only the P atmosphere here. Okay, so the P1 here just include the P. Okay, plus the water here. Okay, water is at this side here, so we get the H1. Okay, this is also this is the oil here. Okay, GH2 is the oil here. Okay, H2, so P oil, P water, H1. Okay, for the H water, and the P mercury here, so we get the H3. So until we get the this one, so we get using the multi-fluid here. Okay, so this is barometer. Atmospheric pressure is measured by a device called a barometer. Thus, the atmospheric pressure is often referred to a barometric pressure. Okay, so measuring atmospheric pressure with a barometer also use the same as I mentioned, because this just using the P atmosphere is through GH here. Okay, so this is the quiz. Okay, quiz 2 here. Consider a double fluid manometers as shown in figure 2. If H1 is 50 cm, H2A and the PB is to calculate the pressure at A. Okay, that's all. Thank you. Okay, tengok dulu.